Dissimilar metal weld, or DMW, cracking damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of dissimilar metal weld, or DMW, cracking based on API 571. Cracking of dissimilar metal welds occurs in the ferritic, carbon steel or low alloy steel, side of a weld between an austenitic, 300 series SS or nickel base alloy, and a ferritic material operating at high temperature. Cracking can result from creep damage, from fatigue cracking, from sulfide stress cracking or hydrogen disbonding. See Figure 4.33. Two primary DMW configurations. Figure 4.33a is ferritic steel pipe, at left side, welded to clad or weld overlaid pipe, at right side. And Figure 4.33b is solid stainless steel pipe, at left side, welded to clad or weld overlaid pipe, at right side. And see this Figure 4.44. Erosion of a 9cr 1mo coker heater return bend. Dissimilar metal weld, or DMW, cracking damage refers to a failure mechanism that can occur at the junction of two different types of metals that have been welded together. This issue is particularly prevalent in applications involving high-temperature and high-pressure environments, such as in power plants, refineries, and nuclear facilities. Characteristics of dissimilar metal weld cracking. Number 1 is material differences. Dissimilar metal weld often involves joining a ferrous metal, such as carbon steel or low alloy steel, with a non-ferrous metal, such as stainless steel or nickel alloys. The differing thermal expansion coefficients, mechanical properties, and chemical compositions of these metals can lead to stress concentrations. Number 2 is cracking locations. Dissimilar metal weld, or DMW, cracking typically occurs at or near the heat-affected zone, HAZ, or the weld itself, where the microstructure has been altered due to the intense heat from the welding process. Cracking can manifest as transverse cracks, longitudinal cracks, or underbead cracks. Number 3 is mechanisms of cracking, such as following. The first is thermal stresses. Discrepancies in cooling rates between the two metal types can induce residual stresses, leading to cracking. The second is hydrogen embrittlement. The welding process may introduce hydrogen into the weld pool, which can migrate to areas of high stress and contribute to cracking. The third is fatigue cracking. Repeated thermal cycling or fluctuating loads can exacerbate stress concentrations, resulting in fatigue cracks over time. Number 4 is consequences. Dissimilar metal weld, or DMW, cracking can compromise the integrity of a structure, leading to leaks, failures, or catastrophic structural collapse. This damage can have significant safety implications and result in costly downtime and repairs. Dissimilar metal weld, or DMW, cracking is a complex failure phenomenon caused by the interaction of different metallic properties at a welded joint. Its prevention and management are critical for maintaining the integrity and safety of engineered systems. This type of dissimilar metal weld, or DMW, cracking typically arises in applications where materials with different thermal and mechanical properties are welded together, such as carbon steel to stainless steel or nickel-based alloys. The fundamental causes of dissimilar metal weld, or DMW, cracking include. Number 1 is thermal expansion differences. The two metals often have different coefficients of thermal expansion, leading to significant stresses when subjected to temperature fluctuations, especially during welding processes. Number 2 is microstructural changes. The heat from welding can create non-uniform microstructures, resulting in zones of brittleness. The heat-affected zone, or HAZ, may exhibit changes that make it more susceptible to cracking. Number 3 is residual stresses. Welding introduces residual stresses in the joint area due to the concentrated heating and rapid cooling involved in the welding process. These stresses can further exacerbate cracking, especially in the presence of tensile loads. Number 4 is hydrogen embrittlement. Often due to the presence of hydrogen in the weld area, exacerbated by the different microstructures of the adjacent metals. Number 5 is composition differences. The difference in alloying elements between the two metals can result in the formation of hard, brittle phases within the weld metal or at the interface, which can initiate cracks. Number 6 is corrosion and environmental factors. Dissimilar metal weld, or DMW, cracking can be aggravated by environmental conditions, such as high temperatures, corrosive environments, or service stresses, which can promote stress corrosion cracking, or SCC, or hydrogen embrittlement. Different corrosion rates and mechanisms in dissimilar metals can lead to localized stress concentrations. The occurrence of dissimilar metal weld, or DMW, cracking is a critical concern in industries like power generation, oil and gas, and petrochemical sectors, where welded joints are subject to rigorous service conditions. It can lead to significant safety hazards, operational downtime, and costly repairs if not properly managed. Preventive measures include careful selection of welding materials, precise control of welding parameters, and thorough post-weld heat treatments to relieve residual stresses and minimize the likelihood of cracking. Regular inspection and monitoring of weld integrity are also essential to detect dissimilar metal weld, or DMW, cracking early and address any potential issues proactively. Dissimilar metal weld, or DMW, affected materials based on API 571. The most common are ferritic materials such as carbon steel and low-alloy steels that are welded to the austenitic stainless steels, as well as any material combinations that have widely differing thermal expansion coefficients. Dissimilar metal weld, or DMW, cracking is a concern in industries that involve welding of different metals, particularly in pressure vessels, piping, and structural components. The affected materials in dissimilar metal weld, or DMW, cracking typically involve a combination of metal types, often characterized by differences in their mechanical properties, thermal expansion coefficients, and metallurgical characteristics. Key affected materials that may be involved in dissimilar metal weld, or DMW, cracking include: Number 1 is carbon steel. This is often used in pipelines and structural components, but may be susceptible to cracking when welded to higher alloy materials. Number 2 is alloy steels. These steels can have varying compositions, affecting their hardness, strength, and susceptibility to cracking. Number 3 is stainless steels. Commonly welded to carbon steels or low-alloy steels, stainless steels can be prone to issues like embrittlement or intergranular corrosion at the weld interface. Number 4 is nickel alloys. These are sometimes used in high-temperature or corrosive environments but may create challenges when welded to lower alloy steels due to differing thermal and mechanical properties. Number 5 is copper alloys. The welding of copper to carbon steel or nickel alloys can lead to significant issues due to differing thermal expansion and conductivity, potentially resulting in cracking. Number 6 is cast irons. When cast iron is joined to steel, the brittle nature of cast iron can result in cracking if not properly handled in the welding process. Number 7 is welding filler metals. The choice of filler metal is crucial as it must match or be compatible with both base materials, and inappropriate selection can lead to weld cracking due to differences in thermal properties or hydrogen susceptibility. Number 8 is other dissimilar metals. Various combinations of metals may also lead to specific cracking mechanisms due to differences in weldability and thermal behavior. The dissimilar metal weld, or DMW, cracking mechanism is influenced by factors such as: Number 1 is differential thermal expansion. Different metals expand and contract at different rates, leading to residual stresses that can precipitate cracking. Number 2 is microstructural changes. Weld heat can cause changes in the microstructure of the affected materials, such as transformation of phases or formation of brittle phases. Number 3 is strain aging. In certain alloys, the presence of dissimilar metals can lead to strain aging, where residual stresses can promote localized cracking. Number 4 is hydrogen embrittlement. The presence of hydrogen during the welding process can lead to cracking, especially in high-strength steels and certain stainless steels. Number 5 is thermal fatigue. Cyclic thermal loading can be more pronounced at the interface of dissimilar metals, leading to fatigue cracking over time. Addressing dissimilar metal weld, or DMW, cracking involves careful selection of welding procedures, filler materials, and post-weld heat treatments, as well as thorough inspection and testing to ensure the integrity of the joints. Dissimilar metal weld, or DMW, cracking critical factors based on API 571. Important factors include the type of filler metal used to join the materials, heating and cooling rate, metal temperature, time at temperature, weld geometry and thermal cycling. The second is cracking can occur because of the different coefficients of thermal expansion between ferritic and austenitic, such as 300 series stainless steel or nickel base alloys, which differ by about 25 to 30% or more. At high operating temperatures, the differences in thermal expansion leads to high stress at the heat-affected zone on the ferritic side. The third is as the operating temperature increases, differential thermal expansion between the metals results in increasing stress at the weldment, particularly if a 300 series SS weld metal is used. Ferritic/austenitic joints can generate significant thermal expansion/thermal fatigue stresses at temperatures greater than 510 degrees Fahrenheit, or 260 degrees Celsius. The fourth is thermal cycling aggravates the problem. Stresses during startup and shutdown can be significant. The fifth is stresses acting on the weldment are significantly higher when an austenitic stainless steel filler metal is used. A nickel base filler metal has a coefficient of thermal expansion that is closer to carbon steel, resulting in significantly lower stress at elevated temperatures. The sixth is for dissimilar welds that operate at elevated temperatures. The problem is aggravated by the diffusion of carbon out of the heat-affected zone of the ferritic material and into the weld metal. The loss of carbon reduces the creep strength of the ferritic material heat-affected zone, thereby increasing the cracking probability. The temperature at which carbon diffusion becomes a concern is above 800 degrees Fahrenheit to 950 degrees Fahrenheit, or 427 degrees Celsius to 510 degrees Celsius, for carbon steels and low alloy steels, respectively. See Figure 4:35, high magnification photomicrograph of a dissimilar metal welds, or DMW, joining a ferritic alloy, or SA213T22, used in high temperature service. Creep cracks, or black specks, can be observed in the ferritic alloy heat-affected zones. Mag. 50X, etched. Dissimilar metal welds on a ferritic steel that are made with a 300 series SS weld metal or a nickel-based filler metal result in a narrow region, mixed zone, of high hardness at the toe of the weld, near the fusion line on the ferritic steel side. These high hardness zones render the material susceptible to various forms of environmental cracking such as sulfide stress cracking or hydrogen stress cracking. PWHT of the weldment will not prevent environmental cracking if the weld is exposed to wet H2S conditions. See Figures 4:36, weld detail used to join a carbon steel elbow, bottom, to a weld overlaid pipe section, top, in high pressure wet H2S service. Sulfide stress cracking, or SSC, occurred along the toe of the weld, arrow, in a narrow zone of high hardness. And 4:37, high magnification photomicrograph of SSC in pipe section shown in Figure 4:36. The eighth is dissimilar metal welds for high temperature service in hydrogen environments must be carefully designed and inspected to prevent hydrogen disbonding. See Figures 4:38. Failure of dissimilar metal welds joining 1.25 Cr 0.5 MO to alloy 800H in a hydrodealkylation, or HAD, reactor effluent exchanger. Crack propagation due to stresses driven at high temperature of 875 degrees Fahrenheit, or 468 degrees Celsius, and a hydrogen partial pressure of 280 sig, or 1.93 MPa. See this Figure 4:39, high magnification photomicrograph of the crack in Figure 4:38 showing blistering and disbondment along the weld fusion line interface. See this Figure 4:40, high magnification photomicrograph of the crack shown above in Figure 4:39. Plastic deformation of the grain structure can be found at the vicinity of the blister. See this figure 4.41, failure of nickel alloy DMW joining HP40, NB modified, tube to 1.25 cr 0.5 mo flange in a steam methane reformer due to cold hydrogen disbonding of the buttering layer. Process temperature 914 to 941 degrees Fahrenheit, or 490 degrees Celsius to 505 degrees Celsius, pressure, 2.14 MPa, H2 content 10 to 20%, off gas. The ninth is in environments that promote liquid ash corrosion, weld cracking problems may be accelerated by stress-assisted corrosion. The ferritic heat-affected zone will preferentially corrode due to the large thermal strain. The results are long, narrow, oxide wedges that parallel the fusion line of the weld, see figure 4.42, when both liquid phase coal ash corrosion and a DMW exists, stress-assisted corrosion of the 2.25 cr 1 mo heat-affected zone may occur. Note that there is a lack of creep damage at the crack tip. Mag. 25X, etched. The 10th is poor geometry of the weld, excessive undercut, and other stress intensification factors will promote crack formation. Dissimilar metal weld, DMW, cracking is a well-documented failure mechanism that can occur at the interface between different types of metals, particularly in structures such as piping in power plants, chemical plants, and oil and gas facilities. Here are some critical factors associated with dissimilar metal weld, DMW, cracking. Number 1 is material properties, such as the following. The first is mechanical properties. The yield strength, ductility, and toughness of the parent metals can significantly affect the cracking potential. Dissimilar metals often have differing mechanical properties that can interact adversely. The second is chemical composition. The alloying elements in different materials can create brittle phases or lead to unfavorable microstructures at the weld interface. Number 2 is welding parameters, such as the following. The first is heat input. The amount of heat introduced during welding can influence the cooling rates and microstructures of the weld and heat-affected zones, HAZ. Higher heat inputs can lead to larger grain sizes and potentially more brittle phases forming. The second is welding procedure. The technique and processes used, including the type of filler material, can affect the metallurgical characteristics of the weld. Number 3 is thermal stress and residual stress, such as the following. The first is thermal cycles. The thermal expansion and contraction during and after welding can induce residual stresses, which may drive cracking. The second is brittle phase formation. The localized thermal effects can lead to the formation of brittle intermetallic compounds, which are more susceptible to cracking under stress. Number 4 is microstructural factors such as the following. The first is weld microstructure. The interaction between different microstructures at the fusion boundary can lead to weak spots. For example, austenitic stainless steel welded to carbon steel might form brittle intermetallic compounds like Fe-Cr or Ni-Fe phases. The second is heat-affected zone, or HAZ, properties. The properties of the HAZ can significantly influence the likelihood of cracking, especially if embrittlement occurs. Number 5 is environmental conditions such as the following. The first is corrosive environments. Dissimilar metal weld, or DMWs, may be more susceptible to stress corrosion cracking, or SCC, if they operate in hostile environments, like high temperature or corrosive media. The second is operating temperature and pressure. Elevated temperatures can enhance diffusion rates, accelerating embrittlement processes. Number 6 is design factors such as. The first is geometric constraints. The design of the weld joint, including the fit-up and joint design, can influence stress concentrations and the potential for cracking. The second is service conditions. The operational conditions, including thermal cycling, mechanical loading, and chemical exposure, can play a significant role in the initiation and propagation of cracks. Number 7 post-weld heat treatment, or PWHT. Properly designed post-weld heat treatment, PWHT, can help relieve residual stresses and transform microstructures to enhance ductility, thereby reducing the risk of cracking. Number 8 is inspection and quality control. Non-destructive testing, or NDT, methods can be critical for detecting early stages of cracking or embrittlement in dissimilar metal weld, DMWs, to allow for preventive actions. Addressing these critical factors during the design, fabrication, and inspection stages can help mitigate the risk of DMW cracking and enhance the integrity and safety of engineered structures. Dissimilar metal weld damage mechanisms affected units or equipment based on API 571. The first is dissimilar metal welds are utilized in special applications in refineries and other process plants. The second is examples of dissimilar metal weld, or DMWs, include welds used to join clad pipe in locations such as transitions in hydroprocessing reactor outlet piping from overlaid low alloy CRMO nozzles or piping to solid 300 series stainless steel pipe. Hydroprocessing exchanger inlet and outlet piping. Alloy transitions inside fired heaters, such as 9CR to 317L in a crude furnace. Hydrogen reformer furnace 1.25 CR inlet pigtails to alloy 800 sockelets or weldolets on hydrogen reformer tubes. Hydrogen reformer furnace alloy 800 outlet cones to CS or 1.25 CR refractory line transfer lines. Alloy transitions inside fired heaters, e.g. 9CR to 317L in a crude or vacuum furnace. Welds joining clad pipe sections to themselves or to unclad carbon or low alloy steel pipe, such as alloy C276 clad CS piping in crude unit overhead system. Nickel base alloy welds joining socket weld valves in 5 and 9 CR piping systems. 300 series SS weld overlay in numerous refinery reactors and pressure vessels. Similar dissimilar metal weld, or DMWs, have been used in FCCU reactors and regenerator vessels and in coker units. The third is all superheaters and reheaters that have welds between ferritic materials, 1.25 CR, 0.5 MO and 2.25 CR, 1 MO, and the austenitic materials, 300 series SS, 304H, 321H and 347H. Dissimilar metal weld, DMW, cracking is a significant damage mechanism primarily associated with the welding of dissimilar metals, such as those typically found in power generation and chemical processing industries. The most affected units or equipment typically include: Number 1 is piping systems. These often consist of carbon steel or low alloy steel connected to stainless steel components. The welded joints between dissimilar metals can be prone to cracking. Number 2 is pressure vessels. Similar to piping, pressure vessels may contain dissimilar metal welds at various connections, particularly where stainless steel is connected to carbon steel. Number 3 is heat exchangers. The joints between different metal types in heat exchangers, especially those using stainless steel and carbon steel, can be susceptible to dissimilar metal weld, DMW, cracking. Number 4 is boilers. Dissimilar welds can occur in boiler components where different materials are used, leading to cracking issues under high temperatures and pressures. Number 5 is reactor vessels. In chemical processing, where reactors may involve dissimilar metals, the welds can suffer from the dissimilar metal weld, DMW, cracking mechanism. Number 6 is turbines and rotating equipment. The interface between dissimilar materials in turbine components can also be affected, particularly in sections where different metals are joined to optimize properties like corrosion resistance or strength. Number 7 is nuclear power plant components. Dissimilar metal welds are particularly a concern in nuclear applications, where the combination of high-stress environments and dissimilar materials can exacerbate cracking. Number 8 is heat transfer and separators. Equipment such as fin-fan coolers, separated by diverse metal types, are also potential sites for dissimilar metal weld, DMW, cracking. Number 9 is high-temperature equipment. Equipment operating at high temperatures, such as gas turbines, as mentioned in the point number 6, and jet engines, can experience dissimilar metal weld, DMW, cracking in the weld joints. Number 10 is desalination plants. the weld joints in equipment used in desalination plants, such as those made of dissimilar metals, can be affected by dissimilar metal weld, DMW, cracking. Factors contributing to dissimilar metal weld, DMW, cracking. Number 1 is differences in thermal expansion and contraction between dissimilar metals. Number 2 is differences in mechanical properties, including yield strength and hardness. Number 3 is environmental factors such as corrosion and stress concentrations. Overall, vigilance in monitoring the integrity of such welds, regular inspection, and employing best practices in welding processes are crucial to mitigating the risks associated with dissimilar metal weld, DMW, cracking. Appearance or morphology of dissimilar metal welds damage mechanisms based on API 571. In most cases, the cracks form at the toe of the weld in the heat-affected zone of the ferritic material, see Figure 4:36 weld detail used to join a carbon steel elbow, bottom, to a weld-overlaid pipe section, top, in high-pressure wet H2S service. Sulfide stress cracking, SSC, occurred along the toe of the weld, arrow, in a narrow zone of high hardness. See Figure 4:37, high magnification photomicrograph of SSC in pipe section shown in Figure 4:36. See Figure 4:38, failure of DMW joining 1.25 Cr 0.5 MO to alloy 800H in a hydrodealkylation, HAD, reactor effluent exchanger. Crack propagation due to stresses driven at high temperature of 875 degrees Fahrenheit, or 468 degrees Celsius, and a hydrogen partial pressure of 280 sig, or 1.93 MPa. See Figure 4:39, high magnification photomicrograph of the crack in Figure 4:38 showing blistering and disbondment along the weld fusion line interface. See Figure 4:40, high magnification photomicrograph of the crack shown above in Figure 4:39. Plastic deformation of the grain structure can be found at the vicinity of the blister. See Figure 4:41, failure of nickel alloy DMW joining HP40, NB modified, tube to 1.25 Cr 0.5 MO flange in a steam methane reformer due to cold hydrogen disbonding of the buttering layer. Process temperature 914 degrees Fahrenheit to 941 degrees Fahrenheit, or 490 degrees Celsius to 505 degrees Celsius, pressure, 2.14 MPa, H2 content 10 to 20%, off gas. See Figure 4:42, when both liquid phase coal ash corrosion and a DMW exists, stress-assisted corrosion of the 2.25 Cr 1 MO heat-affected zone may occur. Note that there is a lack of creep damage at the crack tip. Mag. 25X, etched. The second of appearance or morphology of dissimilar metal damage weld based on API 571 is welds joining tubes are the most common problem area, but support lugs or attachments of cast or wrought 300 series SS to 400 series SS are also affected. Dissimilar metal weld, DMW. Cracking is a type of damage mechanism that can occur at the interface between two different types of metals joined by welding. The appearance or morphology of dissimilar metal weld, DMW, cracking can be characterized by several features. Number 1 is crack location. Dissimilar metal weld, DMW, cracking typically occurs at the weld toe or heat-affected zone, HAZ, where there is a transition between the two dissimilar metals. This is often where thermal stresses and metallurgical differences are most pronounced. Number 2 is crack propagation. The cracks can initiate at the weld interface and propagate either towards the base materials or along the interface. The direction of crack propagation may vary depending on the material properties and environmental conditions. Number 3 is crack shape. Dissimilar metal weld, DMW, cracks can appear as narrow, linear fissures and may be straight or exhibit branching. The surface of the cracks can be relatively smooth but may show signs of secondary cracking or tearing. Number 4 is different crack types. Common types of cracking observed in DMW include: the first is heat-affected zone, HAZ, cracking. this type of cracking often occurs due to residual stresses and microstructural changes in the heat-affected zone, HAZ. The second is hydrogen-induced cracking, HIC, related to the absorption of hydrogen during welding or subsequent processes, leading to cracking within the metal. The third is stress corrosion cracking, SCC, often results from the combination of tensile stress, a corrosive environment, and the presence of dissimilar metals. Number 5 is surface features. The surface of the cracks may exhibit distinct features due to the combination of the two materials' mechanical properties. For instance, cracks may show features typical of both ductile and brittle fracture, such as dimples from ductile tearing or shiny, flat surfaces from brittle fracture. Number 6 is intergranular versus transgranular. Cracking can be intergranular, following the grain boundaries of the metals, or transgranular, cutting through the grains themselves. The type of crack can depend on the service conditions and material properties. Number 7 is edge and root cracking. Cracking may also occur at the edges and root of the weld, which can compromise the integrity of the joint. Number 8 is discoloration and oxidation. Areas surrounding the cracks may show signs of oxidation or discoloration due to high temperatures during welding and subsequent exposure to environmental factors. Number 9 is dimensional characteristics. The cracks may vary significantly in width and depth, influenced by the welding process, the materials involved, and the level of stress or strain experienced in service. Overall, the appearance of dissimilar metal weld, DMW, cracking is influenced by the properties of the dissimilar metals, the welding process, and the operational environment. As such, detailed examination through microscopy or non-destructive testing methods may be required for accurate characterization. DMW damage prevention and mitigation based on API 571. The first is for high-temperature applications. Nickel-based filler metals, which have a coefficient of thermal expansion closer to carbon steel and low-alloy steels, may dramatically increase the life of the joint, because of the significant reduction in thermal stress acting on the steel, ferritic, side of the joint. Refer to API 577 and API 582 for additional information on filler metal selection, welding procedures and weld inspection. The second is if 300 series SS welding electrodes are used, the dissimilar metal weld should be located in a low-temperature region. The third is consider buttering the ferritic side of the joint with the SS or nickel-based filler metal and perform PWHT prior to completing the DMW to minimize the hardness of the mixed weld zone in order to minimize susceptibility to environmental cracking. See Figure 4.34. Figure 4.34. Schematic of typical weld detail used to join a solid stainless steel pipe to a clad or weld overlaid pipe. The sequence is: 1. Butter the weld bevel on the ferritic steel side. 2. Perform PWHT of the ferritic side prior to making dissimilar weld. 3. Complete the dissimilar weld using alloy filler metal. 4. Do not PWHT the completed dissimilar weld. Figure 4.35. High magnification photomicrograph of a DMW joining a ferritic alloy, SA213T22, used in high temperature service. Creep cracks, black specks, can be observed in the ferritic alloy heat affected zones. Mag 50X, etched. The fourth is on buttered joints. The thickness of the weld metal should be a minimum of 0.25 inch, 6.35 mm, after the bevel is machined. Figure 4.35. Figure 4.35, high magnification photomicrograph of a DMW joining a ferritic alloy, SA213T22, used in high temperature service. Creep cracks, black specks, can be observed in the ferritic alloy heat affected zones. Mag 50X, etched. The fifth is in steam generating equipment. The weld at the high temperature end should be made in the penthouse or header enclosure, out of the heat transfer zone. The sixth is for high temperature installations. Consider installing a pup piece that has an intermediate thermal expansion coefficient between the two materials to be joined. Dissimilar metal weld cracking can pose significant challenges, especially in industries such as nuclear, petrochemical, and power generation, where components made from different materials are joined. These welds can suffer from cracking due to differences in thermal expansion, mechanical properties, and corrosion resistance. To prevent or mitigate dissimilar metal weld cracking, several strategies can be employed. Prevention and mitigation strategies for dissimilar metal weld cracking. Number 1 is material selection. Include: the first is choose compatible materials for welding that have similar thermal expansion coefficients, mechanical properties, and corrosion resistance. The second is use filler materials specifically designed for dissimilar metal welding to reduce the likelihood of cracking. Number 2 is welding techniques. Include: the first is use post-weld heat treatment, or PWHT, to relieve residual stresses induced by welding. The second is control welding parameters, such as heat input, speed, and interpass temperature, to minimize distortion and residual stresses. The third is opt for welding processes that produce lower heat input, such as laser welding or plasma arc welding. Number 3 is weld design. Include: the first is design joints to minimize stress concentrations. Use wider grooves and adequate dimensions that accommodate thermal expansion. The second is ensure a proper fit-up to prevent gaps which can lead to incomplete fusion or other defects. Number 4 is pre-weld preparation. Include: the first is thoroughly clean the base materials to remove any contaminants, oils, or oxides. The second is consider using a preheat procedure if applicable. This can help maintain consistent temperatures throughout the weld. Number 5 is monitoring and inspection. Include: the first is use non-destructive testing, or NDT, methods such as ultrasonic testing, or UT, or radiographic testing, or RT, to identify cracks or defects in dissimilar metal welds during and after fabrication. The second is regular monitoring of welded joints in service can help detect early signs of failure. Number 6 is post-weld processing. Include: the first is implement PWHT as needed to reduce hardness in areas of a weld that could be susceptible to stress corrosion cracking. The second is use techniques like stress relief grinding on vulnerable areas if applicable. Number 7 is environmental control. Include: the first is ensure that the environment in which the weld is made is suitable. For instance, welding in humid conditions can lead to increased risk of hydrogen-induced cracking. The second is, if appropriate, consider applying protective coatings or corrosion inhibitors. Number 8 is training and certification. The first is ensure that welders are properly trained and qualified for DMW work. Specific training can help them understand the nuances of welding dissimilar metals and the associated risks. Number 9 is engineering analysis. Conduct stress analysis to evaluate the effects of operating conditions, thermal cycles, pressure, etc., on welded joints and to ensure the design can withstand expected service conditions. Implementing these strategies can help minimize the risk of dissimilar metal welds cracking and extend the service life of welded components in various high-stress environments. Inspection and monitoring of thermal shock based on API 571. The first is the following elements should be considered for non-destructive examination of critical dissimilar but welds before they are put into service. They are: 100% PT after buttering and completion, 100% UT on butter layer after PWHT, check bonding, 100% RT 100% UT recordable, and PMI. The second is for dissimilar welds in fired heater tubes. RT and UT shear wave inspection should be performed. The third is environmental cracking will also result in surface breaking cracks initiating on the ID surface exposed to the corrosive environment, which can be detected using WFMT or external SWUT methods. Dissimilar metal weld, or DMW, cracking damage refers to the issues that can arise at the junction of two different types of metals that are welded together, commonly seen in applications like piping systems in power plants and refineries. Detecting this type of damage is critical to maintaining structural integrity and safety. Various inspection and monitoring methods can be employed to detect dissimilar metal weld, or DMW, cracking damage. Number 1 is visual inspection, or VT. A basic but vital step, visual inspections can help identify surface cracks, discoloration, or other signs of degradation. This method relies on trained inspectors to recognize potential issues. Number 2 is magnetic particle testing, or MT. This method is used for detecting surface and near-surface discontinuities in ferromagnetic materials. Magnetic particles are applied to the surface, any cracks will distort the magnetic field and cause the particles to cluster, revealing the flaw. Number 3 is dye penetrant inspection, or PT. It involves applying a dye to the surface of the weld. The dye penetrates any cracks or defects. After a developing agent is applied, the dye will highlight the cracks under UV or visible light. Number 4 is ultrasonic testing, or UT. High-frequency sound waves are sent through the material. Reflections off cracks or defects can be detected, providing information about the size and location of flaws, including those in dissimilar metal welds. Number 5 is radiographic testing, or RT. X-rays or gamma rays penetrate the weld and the resulting images reveal internal flaws. This method can show the quality of the weld and any internal cracking or voids. Number 6 is eddy current testing, or ECT. Particularly useful for non-ferromagnetic materials, eddy currents induce localized electromagnetic fields that change near cracks or defects. This method is effective for detecting surface and subsurface cracks. Number 7 is thermography. Infrared thermography can detect heat variations on the weld surface during operation, which may indicate crack presence or material degradation through variations in thermal conductivity. Number 8 is acoustic emission testing, or AET. This method monitors the high-frequency waves produced by crack growth and other changes in the material under stress. It can help detect the onset of cracking in real time. Number 9 is digital imaging and advanced analysis techniques. Techniques like digital X-ray or high-resolution computed tomography, or CT, can provide more detailed imaging and help in assessing the growth of cracks over time. Number 10 is fiber optic sensors. These sensors can be embedded or placed near the weld, providing continuous monitoring of strain, temperature, and any changes indicative of cracking. Number 11 is combined methods. Often, a combination of the above techniques is used to enhance detection accuracy and reliability. For example, initial visual inspections may be supplemented with ultrasonic testing for more detailed assessment. Recommendations for inspection programs. Number 1 is regular inspection intervals should be established based on risk assessments, potential operational stresses, and history of material behavior. Number 2 is employ personnel with proper qualifications and training in inspecting dissimilar metal weld, or DMWs. Number 3 is maintain documentation of inspections, findings, and subsequent actions for compliance and tracking potential issues over time. Utilizing an appropriate selection of these methods based on the specific application, environment, and operational demands can greatly enhance the detection and management of dissimilar metal weld cracking issues. Thank you.